Hi, in this session, we will discuss about different graphic elements in VTK and learn how to manage them to visualize data. In our last session, we learned how VTK Interactor Style class is used to process user events, like mouse clicks and movements. Now let us understand how event-driven mechanism is used in VTK. Events represent specific occurrences or actions, such as mouse clicks, key presses, timer ticks, or custom events triggered by the application, while observers are objects that listen for specific events and execute callback functions when those events occur. They can be attached to various VTK objects, such as renderers, render windows, actors, interactor styles, and custom classes, to perform custom actions or update the application state. VTK provides a wide range of predefined events with unique identifier that cover interactions with the rendering window, user inputs, and other system events. By using events and observers in VTK, we can create interactive and responsive visualizations, handle user inputs, and update the rendering based on changes in the application state. Now, let's take an example where we want to perform an operation when the user presses a specific key on the keyboard. First, we have to define a callback function with appropriate arguments. The obj argument refers to the object that triggered the event, and event argument is the event identifier. Inside the callback function, we include code to handle the key press event. After defining the observer function, we attach it to a VTK object using addObserver method to listen for specific events and trigger the callback function defined for that event. Now, let us understand the VTK Interactor Style class. It is a class that defines the behavior of user interactions, such as mouse and keyboard events, within a rendering window. It is an abstract base class. We have to use the derived class variations such as VTK Interactor Style Trackball Camera class to define how the camera behaves in response to mouse movements in VTK window. It supports camera manipulation operations such as zooming, panning, rotating, and camera settings. We can also customize the behavior of an interactor style by subclassing it and overriding its methods, or add additional functionality in response to user events. VTK Interactor Style Trackball Camera is a class that provides a trackball style interaction for manipulating the camera in a 3D scene. This interaction style allows users to rotate, zoom, and pan the camera using mouse movements. Now, to associate an interactor style with the render window interactor, we use the function setInteractor and pass the interactor style object. Users can rotate the camera around the scene by clicking and dragging the mouse. Scrolling the mouse wheel zooms the camera in or out, adjusting the field of view. Holding down middle button and dragging the mouse pans the camera horizontally and vertically. In this class, there are virtual event handling methods, which we can override in our custom implementation of the interactor style, and customize the way we interact with the rendered scene. Creating a custom interactor style allows us to define specific behaviors and interactions for our application needs. Here's an example of how we can create a custom interactor style by subclassing VTK Interactor Style Trackball Camera class and overriding its methods and defining custom logic for user interaction. Then we just have to set our custom interactor style in the render window interactor, so all the events are passed to our interactor class and handled using the overridden methods. VTK uses VTK Camera class to represent the camera, which is responsible for projecting a three-dimensional scene onto a two-dimensional plane. There are two projection methods in computer graphics. They are orthographic projection and perspective projection. In orthographic projection, also called as parallel projection, the light entering the camera is parallel to the projection direction. The viewing volume is defined by near and far clipping planes. Objects in between the near and far clipping planes are visible to the user. VTK Camera class also provides many functions to control camera movement, such as yaw, pitch, and zoom. When we initialize the render window, the renderer class internally creates a default camera, which we can access using getActiveCamera function. Then we can use the camera object to set its properties like position, focal point, and view up vector. When we interact with the renderer, using the mouse, the interactor class also manipulates these camera settings, and the scene is redrawn to reflect the changes in the camera. The default focal position of camera is at the origin of the world coordinate system. By using these functions from the VTK camera class, we can position the camera in the 3D space to create orthographic projections of the 3D object. Coordinate systems play a crucial role in computer graphics and visualization. They define how position, orientation, and transformation of 3D objects are represented and manipulated within a 3D environment. There are 4 coordinate systems commonly used in VTK. Model coordinate system, which is attached to individual objects or actors in the scene. Each object has its own local coordinate system. All transformations applied to objects, such as translations, rotations, and scalings, are usually done in the object's local coordinate system. World coordinate system is the global coordinate system that defines the overall space in which objects are placed and visualized. It is used for defining the absolute position of objects, cameras, and lights within the scene. The view coordinate system is used in rendering pipelines to map 3D coordinates to 2D screen coordinates for display. VTK's rendering pipeline performs transformations from world coordinate system to view coordinate system during rendering to project objects onto the screen. Display is the coordinate system of the screen or viewport where the rendered image is displayed. It is a 2D coordinate system, with the origin at the top left corner, and positive x-axis extending to the right, and positive y-axis extending downwards. VTK axis actor class creates a trihedron that includes 1 origin, 3 axes, and 3 labels. It is used for visual representation of coordinate axes that helps orient objects in a 3D scene by showing the directions of the x, y, and z axes. Now, to create the trihedron, we define a function as makeAxisActor. Then, we create an object named axis, a VTK axis actor class, which represents the coordinate axes. Then, we set the text and length of all the 3 axes. We can adjust other geometric parameters of the trihedron, like radius of the cone and cylinder of the axes. Then, axis object is added to the VTK renderer using the addActor method. When we run this code, we see the coordinate axes displayed in the render window, helping us to visualize the x, y, and z directions within our scene. Lights are crucial for illuminating the scene and enhancing the visual quality of rendered objects. Lights simulate various lighting conditions, such as ambient light, directional light, point light, and spotlights, which contribute to the overall appearance of the scene. Ambient light is a uniform background light that illuminates all objects in the scene equally. It helps provide a basic level of illumination and prevents scenes from appearing completely dark. Directional lights simulate light coming from a specific direction, such as sunlight. They have a direction but no specific position in the scene. Point lights simulate light originating from a specific point in space, radiating in all directions. They are useful for creating localized light sources, such as lamps or light bulbs. Spotlights simulate focused light beams with a specific direction, position, and cone angle. They are ideal for creating effects like flashlight beams or highlighting specific areas. Now, we create a directional light pointing in the Y direction, with a sky blue color and with full intensity. For directional light, we also need to define type of light as headlight. A headlight is always located at the camera, and is pointed at the camera's focal point. To define a spotlight, we have to adjust the cone angle, and also set the position of the cone. We have to adjust the parameters as needed for our visualization, and add all light objects to the renderer, using addLight method. VTK has many widgets which allow users to interact with the rendered scenes. Widgets are subclasses of VTK Interactor Observer class, and they respond to mouse and keyboard events, invoked by VTK Render Window Interactor. VTK provides numerous widgets to perform tasks that range from measurements and annotations to segmentations, scene parameter manipulation, and much more. Widgets from old architecture are derived from VTK 3D Widget class, whereas new widgets are derived from VTK Abstract Widget class. We will learn how to use these widgets later in our series. Please do like the video and subscribe to our channel to stay updated for our latest videos. Thank you.